Unit 8, Physical and Chemical Equilibrium. Learning Objectives. After studying this unit, the students will be able to describe the meaning of equilibrium, explain the dynamic nature of equilibrium involved in physical and chemical processes, state the law of mass action, deduce the expression for equilibrium constants Kc and Kp, establish the relationship between Kp and Kc, predict the extent of reaction using equilibrium constant, state Le Chatelier's principle, explain the effect of various factors that affect a system of equilibrium, derive Van't Hoff equation. Claude Louis Berthollet, a Savoyard French chemist, studied the mechanism of reversible chemical reaction and developed the theory of chemical equilibria. He also contributed to modern chemical nomenclature. He was the first to demonstrate the bleaching action of chlorine gas and developed a solution of sodium hypochlorite that acts as a bleaching agent. Eight point one Introduction. In our daily life, we observe several chemical and physical changes. For example, a banana gets ripened after few days, silver gets tarnished in few months, and iron gets rusted slowly. These processes proceed in one direction. Now let us consider the transport of oxygen by hemoglobin in our body as an illustration for a reversible change. The hemoglobin combines with oxygen in lungs to form oxyhemoglobin. The oxyhemoglobin has a tendency to form hemoglobin by releasing oxygen. In fact, in our lungs, all the three species coexist. Few chemical reactions proceed in only one direction, whereas many reactions proceed in both the directions, and these reactions are called reversible reactions. In chemical reactions, the concentration of the reactants decreases and that of the products increases with time. In reversible reactions, initially the reaction proceeds towards the formation of the product. Upon formation of the product, the reverse reaction begins to take place. At a particular stage, the rate of the reverse reaction is equal to that of the forward reaction, indicating a state of equilibrium. It is desirable to know the three crucial aspects of chemical reactions, namely the feasibility, the rate of the reaction, and the extent of reaction. We know that the feasibility of a reaction is given by thermodynamics. Chemical kinetics will tell about the rate of the reaction. The equilibrium constant tells about the extent of a reaction, which we will discuss in this chapter. We will also discuss the types of equilibrium, the significance of equilibrium constant, and its relationship to thermodynamic quantities, and the response of chemical equilibrium to change in the reaction conditions. 8.2 Physical and Chemical Equilibrium. There are different types of equilibrium. For example, if two persons with same weight sit on opposite sides of a seesaw at equal distance from the fulcrum, then the seesaw will be stationary and straight and it is said to be in equilibrium. Figure 8.1 Illustration of equilibrium. Another example of a state of equilibrium is the game of tug of war. In this game, a rope is pulled taut between two teams. There may be a situation when both the teams are pulling the rope with equal force and the rope is not moving in either direction. This state is said to be in equilibrium. Figure 8.2, tug of war. In reversible processes, the rate of two opposing reactions equals at a particular stage. At this stage, the concentration of reactants and products do not change with time. This condition is not static and is dynamic because both the forward and reverse reactions are still occurring with the same rate. 8.2.1, Physical equilibrium. A system is said in which the amount of matter constituting different phases does not change with time is said to be in physical equilibrium. This involves no perceptible physical change in the system. To understand the physical equilibrium, let us analyze the following phase changes. Solid to liquid equilibrium. Let us consider the melting point of ice in a closed container at 273 Kelvin. This system will reach a state of physical equilibrium in which the amount of water in the solid phase and liquid phase does not change with time. In the process, the total number of water molecules leaving from and returning to the solid phase at any instant are equal. If some ice cubes and water are placed in a thermos flask at 273 Kelvin and 1 atm pressure, then there will be no change in the mass of ice and water. At equilibrium, rate of melting of ice is equal to rate of freezing of water. H2O in solid state gives H2O in liquid state. The above equilibrium exists only at a particular temperature and pressure. The temperature at which the solid and liquid phases of a substance are at equilibrium is called the melting point or freezing point of that substance. Liquid vapor equilibrium. Similarly, there exists an equilibrium between the liquid phase and the vapor phase of a substance. For example, liquid water is in equilibrium with its vapor at 373 Kelvin and 1 atmospheric pressure in a closed vessel. H2O in liquid form gives H2O in gaseous form. Here, rate of evaporation is equal to rate of condensation. The temperature at which the liquid and vapor phases are at equilibrium is called the boiling point and condensation point of the liquid. Solid vapor equilibrium. Consider a system in which the solid sublimes to vapor. In this process also, equilibrium can be established between these two phases. When solid iodine is placed in a closed transparent vessel, after some time the vessel gets filled up with violet vapor due to sublimation of iodine. Initially, the intensity of the violet color increases. After some time, it decreases and finally it becomes constant as the following equilibrium is attained. I2 in solid state gives I2 in gaseous state. More examples. Camphor in solid state gives camphor in gaseous state. NH4Cl in solid state is in equilibrium with NH4Cl in gaseous state. Equilibrium involving dissolution of solids or gases in liquids. Solid in liquids. When you add sugar to water at a particular temperature, it dissolves to form sugar solution. If you continue to add much sugar, you will reach a stage at which the added sugar remains as solid and the resulting solution is called a saturated solution. Here, as in the previous cases, a dynamic equilibrium is established between the solute molecules in the solid phase and in the solution phase. Sugar in solid condition is in equilibrium with sugar in solution condition. In this process, rate of dissolution of solute is equal to rate of crystallization of solute. Gas in liquids. When a gas dissolves in a liquid under a given pressure, there will be an equilibrium between gas molecules in the gaseous state and those dissolved in the liquid. Example, in carbonated beverages, the following equilibrium exists. CO2 gaseous state is in equilibrium with CO2 solution. Henry's law is used to explain such gas solution equilibrium processes. Next, 8.3 Chemical equilibrium. Similar to physical processes, chemical reactions gradually attain a state of equilibrium after some time. Let us consider a general reversible reaction. A plus B gives C plus D. Initially, only A and B are present. Soon, a few molecules of the product C and D are formed by the forward reaction. As the concentration of the products increases, more products collide and react in the backward direction. This leads to an increase in the rate of backward reaction. As the rate of reverse reaction increases, the rate of the forward reaction decreases. Eventually, the rate of both reactions becomes equal. X-axis time, y-axis reaction rate. This curve is forward rate, reverse rate, and here we have equal rates. Figure 8.3 Attainment of equilibrium state for the variation of the rates of forward and backward reactions with time. Products, reactants, equilibrium, no change in amounts. Blue color goes like this and red color reactants goes like this. 8.4 Dynamic nature of equilibrium. Let us consider a situation in multi-story building. People are moving from first floor to second floor and vice versa. Assume that a certain number of people moves up from first floor to second floor in a specific time, and the same number of people moves down from second floor to the first floor in the same time. Now, the rate of movement of people from first to second floor equals the rate of movement of people from second to first floor, and hence the number of people in each floor will remain the same. Thus, the population of people on the two floors is in a dynamic equilibrium. Let us extend this analogy to understand dynamic nature of equilibrium. Chemical reactions which are reversible do not cease when equilibrium is attained. At equilibrium, the forward and the backward reactions are proceeding at the same rate and no macroscopic change is observed. So, chemical equilibrium is in a state of dynamic equilibrium. For example, hydrogen in gaseous state plus iodine in gaseous state gives 2Hi in gaseous state.